Swayam Prabha. Digital India. Educated India.
Hello everyone, this is the lecture 4 of module 12. So in this lecture 4 we are going to have a little bit of taste of numerical problems in seismology, and this is the part 1 where we are going to discuss 4 problems. That means the 4 questions that are numerical in nature. So this is the numerical problems part 1. The question number 1 that says that calculate the stress and strain tensors for these two cases where monochromatic, that means a single frequency plane wave, are traveling in x direction in a medium with homogeneous and isotropic properties. The two cases are, first case is p wave, for which the displacement as a function of x is given a sine omega t minus kx. So you can see this is traveling wave which is traveling in positive x direction. And then there is another case for S wave where u displacement as a function of y direction is a sine omega t minus kx. So you can see the wave is traveling in x direction but the displacement are in y direction. So we are going to solve this numerical here, and we'll see how the stress and strain tensors for these two cases can be calculated. So let's discuss about case number 1 here. And in this case number 1, for the p wave we have ux, that is equal to a sine omega t minus kx, and uy and uz both are basically equal to 0 since the ray is traveling in x direction and the displacement that is given in x direction only. So we can define the strain tensor. So the strain tensor can be written as E sub ij, that will be equal to, we have seen this particular matrix before. It says that del ux by del x and half del ux by del y plus del uy by del x, and the next component is half del ux by del z plus del uz by del x. Likewise for this one, half in bracket del uy by del x plus del ux by del y, and this one del uy by del y, and here you have half del uy by del z plus del uz by del y, and here you have half in bracket del uz by del x plus del ux by del z, half del uz by del y plus del uy by del z. Here you have half in bracket, which should be like this here, del uz by del z. And this is the matrix for the strain tensor, but we can note that the uy and uz both are equal to 0 since the displacement are happening in x direction only. So you can, and we also know that ux is only a function of x, so is only a function of x, so we can write del ux by del y is equal to del ux by del z is equal to 0. Hence what we need to calculate, we need to calculate only del ux by del x, that is del by del x, and we know ux is a sin omega t minus kx. So when you will solve this del ux by del x will come equal to minus of ka cos omega t minus kx. So this is the del ux by del x. So we can write E11 is equal to minus of Ka cos omega t minus Kx. So this is the expression for E11, and the other all other components will be 0, and all other components or elements are 0, right? And we need to get stress also, so this is the strain, and other all component will be 0 for the first case. And to get stress, we can use the relationship sigma ij is equal to lambda theta delta ij, this is the Kronecker delta function, plus 2 mu eij. And there are no shear strain, so only component that we need to worry about are the diagonal component here. And for that case we can calculate the theta term, that is theta which we need to calculate here, and this theta is equal to del ux by del x plus del uy by del y plus del uz by del z, and that will come out to be, since we have only this component non-zero and other components are basically equal to 0, so you are left with minus Ka cos omega t minus Kx. So this is the stress for the case 1. Now let's look at the case 2. And case 2, it says that as wave, the displacement in y directions are given, that is for the wave as wave traveling in x direction, a sin omega t minus kx. So now let's solve the case B. And for the case B, what is given? For the S wave, the displacement uy is given a sin omega t minus kx. So this is given, and now we need to calculate the strain, and since we know that the displacement is in the y direction and that wave is traveling in x direction, so we can write ux is equal to uz is equal to 0. So we can write, so del uy by del x is equal to del by del x, and that we need to calculate in bracket a sin omega t minus of kx, and that is equal to minus ka cos omega t minus kx, and all other derivatives will be 0. All other derivatives are 0. So strain tensor we can calculate Eij will be equal to, in matrix form, 0 half in bracket minus Ka cos in bracket omega t minus kx, and then 0, and half minus Ka cos omega t minus kx, that is 0 and that is also 0, and here is 0, 0 and 0. Now we need to get the value of the stress. So to get stress, note we know that the theta is equal to 0. So sigma will be equal to, from the equation that we just saw, from this equation. So you are left with minus half Ka cos omega t minus of kx, and in bracket you will be having 0, 2 mu 0, and then you will be having 2 mu 0, 0 and 0, 0 and 0. So this is the solution for this particular question, where we had the two cases. For P wave we need to calculate stress and strain tensor. For S wave also we need to calculate stress and strain tensor. So the solution goes like this, we have just saw. Now let's look at the next example, where it says that this is the problem number 2. So give me a specific example of a deformation function ux where total dilatation is 5 for all values of x. So basically, if you look at the dilatation, this is the dilatation, and this dilatation is basically theta, that is equal to Eij, and that is equal to del u1 by del x1 plus del u2 by del x2 plus del u3 by del x3, and that is can be written as del dot u vector. And so we just need to basically come up with a function where the derivatives sum up to basically 5. So this is what it is asked. The sum of all these derivatives should be equal to 5, and that may happen for a various or the plenty number of options, and here is one of the option. So we can write, so we just need to come up with a function where the derivatives add up to 5. There are basically plenty of options. You can write there are many options for doing so, and we can write like here is one, and that is like, let's suppose if you take one example, one such example is 5x1. So when you will do theta, that is Eij for del u1 by del x1, so when you will do del by del x1 of 5x1 plus del of del x2 5x1 plus del of del x3 of 5x1. So what you will see, this will become 5, and other terms, this one and this one, will become 0 plus 0, so you will get 5. Likewise you can have ux is equal to 5x2 5x3, so those will give you the total dilatation, that is equal to 5. Now look at the next problem, that is the problem number 3. The problem number 3 says that two guitar strings are attached and pulled taut with a tension of 50 Newton. String 1 has a density of 3.5 into 10 to the power minus 3 kilogram per meter. String 2 R has a density of 5 into 10 to the power minus 4 kilogram per meter. A wave with initial amplitude 0.1 millimeter and a wavelength of 5 centimeter propagates down string 1 and interact with string 2. So now they have asked some questions A to F. Question number 1 is, what is the amplitude of the transmitted wave in string 2? What is the amplitude of reflected wave in string 1? What is the sum of reflection and the transmission coefficient? What is the wavelength of the transmitted wave? What is the energy flux in string 1 before any energy enters into string 2? What is the energy flux for the reflected and the transmitted wave? Don't worry about the direction of the energy travel. That means assume both the reflected and the transmitted energy flux has the same sign. So now let's solve the question number A, that is, what is the amplitude of the transmitted wave in string 2? For that purpose, we need to first calculate the velocity in string 1 and a velocity in string 2. So now let's talk about it and solve it. Question number A. For this we need to first calculate V1 and V2. So V1 will be equal to, in bracket, tau by rho to the power 1 by 2. This formula we have seen while solving for the 1D wave equation, and we have seen the tension is given, that is 50 Newton, and the string density is given 3.5 into 10 to the power minus 3, and when you will incorporate for V1, that means like 50 kilonewton into 10 to the power 3 Newton divided by rho, that is 3.5 into 10 to the power minus 3, 3.5 into 10 to the power minus 3. So when you will solve this, then you will get 119.5 meter per second. Likewise, you can calculate velocity in string 2, that is V2, and that can be given by tau by rho to the power 1 by 2, and that will be equal to, so you know the tau is 50 Newton and the string 2 density is given, so 50 divided by 5 into 10 to the power minus 3 to the power 1 by 2. So when you will solve it, then you will get the velocity V2, that is equal to 316.2 meter per second. Now we need to calculate what is the amplitude of the transmitted wave in string 2. So that means we are supposed to calculate first the transmission coefficient. So for the transmission coefficient we need the value of impedance in both of the strings. So impedance I1 in first string 1 is rho 1 and V1, that will be equal to, when you will multiply, you will get 0.4183 kilogram per meter cube into meter per second. Likewise, if you will calculate impedance in second string, that will come out to be rho 2 V2, and that will be equal to 0.1581, that is kilogram per meter cube into meter per second. So now you can calculate the transmission coefficient, and that is equal to 2 I2 divided by I1 plus I2. and that will come out to be, when you will incorporate the value, 1.4514. So now amplitude in the second string will be equal to the transmission coefficient and multiplied by the value that is given, the initial amplitude 1.1 millimeter. So that basically come out to be 1 into 10 to the power minus 4 meter, and when you will solve, it will come out to be 1.4514 into 10 to the power minus 4 meter. So this is the amplitude. And then in the string 2, now we need to calculate the amplitude of reflected wave in string 1. So question number B. So what is the amplitude of the reflected wave in string 1? So first we need to calculate the reflection coefficient, that is I1 minus I2 divided by I1 plus I2, and that will come out to be 0.4514. And if you want to calculate the amplitude, then amplitude will be equal to 1 into 10 to the power minus 4 meter initial amplitude of the incident wave into reflection coefficient, and that will come out to be 4.514 into 10 to the power minus 5 meters. Now the next question is, what is the sum of reflection and transmission coefficient? So this question we need to solve. What is the sum of reflection and transmission coefficient? So see, the sum is R plus T, and that will be equal to 1.9028. Now let's talk about question number D. Question number D says that what is the wavelength of the transmitted wave? So for this, what we are going to do, we will solve it like V1 into 2 pi by lambda 1 is equal to V2 into 2 pi by lambda. So when we solve it, lambda 2, sorry. So when will we solve it? So this will imply lambda 2 will be equal to V2 into 2 pi lambda 1 divided by V1 2 pi, and this will give you V2 by V1 into lambda 1, and that will come out to be 0.1323 meter. Likewise, question number E, and question number E says that what is the energy flux in string 1 before any energy enters into string 2? So for this, the energy flux formula, so energy flux formula is this: E dot A square omega square rho 1 V1 by 2, and for that we need to calculate for string 1. So before any energy enters into string 2, that means you are taking the incident wave energy amplitude, and then you are multiplying it with the square of the angular frequency density of string 1, then velocity in string 1, and divided by 2. So you know that the amplitude is 0.1 millimeter. So 0.1 into 10 to the power minus 3 whole square into, we need to calculate the angular frequency, and for angular frequency we can calculate the 2 pi, angular frequency is 2 pi by t, or you can say 2 pi nu, that can be calculated, and then you can calculate, you have the velocity, you know the values of rho 1 and v1 divided by 2. When you will solve it, you will get it as 0.4719, and that is second minus square kilogram per meter and meter per second, and that will come out to be joule by meter per second. Likewise, we can calculate the last question. Last question asks that what is the energy flux for the reflected and transmitted waves Don't worry about the direction of the wave energy, and that means both the reflected and the transmitted energy flux has the same sign. So now ER dot we need to calculate, and that will be equal to amplitude into reflection coefficient square, that is omega square rho 1 V1 by 2, that we need to calculate, and when you will calculate it, it will come out to be 0.0962 joule by meter second. Likewise for the transmitted wave, that will be A into T square omega square rho 2 V2 by 2, and that will come out to be 0.3757 joule by meter second. Now let's solve the last question. Here in the last question it is said that assume a harmonic P wave is traveling through a solid with velocity alpha is equal to 10 km per second. If the maximum strain is 10 to the power minus 8 unit, what is the maximum particle displacement for wave with periods 1 second, 10 second and 100 second? And we can assume that the P wave is moving in x direction. So U vector is equal to A e to the power iota omega t minus kx, comma 0 and comma 0. So what we can do to solve this question, let's assume the P wave is moving in the x direction, then Ux is equal to A e to the power iota omega t minus kx, and Uy is equal to Uz, that is equal to 0. So and also we are given wave periods that is of t is equal to 1, 10 and 100 seconds. So we can calculate the strain. So strain Eij, we know the matrix, we can write it again. The matrix says that del Ux by del x half del Ux by del y plus del Uy by del x plus half del Ux by del z plus del Uz by del x, and here you have half del Uy by del x plus del Ux by del y, and there you have del Uy by del y, and here you have half del Uy by del z plus del Uz by del y, and here you have del Uz by del z, and here you have half in bracket del Uz by del x plus del Ux by del z half del Uz by del y plus del Uy by del z, and that is the matrix of strain tensor. So there is only one non-zero term, that is maybe we can write like the only term here that is non-zero is, so del Ux by del x is equal to del by del x in, so this is A e to the power iota omega t minus kx that we need to solve, and this will become minus iota k a e to the power iota omega t minus kx. So now note that to find out the maximum strain, so note that the strain is maximized when omega t minus kx is equal to pi by 2, right? Then minus iota ka e to the power minus e to the power iota pi, that is equal to ka. So ka is equal to 10 to the power minus 8. So this is what it is given in the question. The maximum strain is 10 to the power minus 8. So k is equal to minus 10 to the power minus 8. So which implies that k is equal to, or we can say that, so k is equal to 2 pi by lambda, and that is equal to 2 pi by alpha t. Alpha is the wave velocity, and then we can write 2 pi by we need to find out it for 10, 100, 1000 kilometers. So basically the value of a will be 10 to the power minus 8 divided by k vector, and that is basically you can say 1.59 into 10 to the power minus 6, 10 to the power minus 7, 10 to the power minus 8 kilometers, right? Now we can solve. So this is the answer to this particular question, that we need to figure out the what is the maximum particle displacement at 1 second, 10 second and 100 second, and this is the displacement that we can calculate it for. So now this is the problem number 4 that we wanted to solve it for, and I hope you might have understood all the problems that was discussed in this particular lecture, and these are the references, and thank you so much. Bye bye.